Okay, capacitors continued. Charging and discharging graphs. Now, this arose in yesterday's lesson when I didn't think that the graphs that I prepared for you were clear enough. And I wanted to just introduce you to the most simple possible charging and discharging scenario. So, if I just start off with a circuit that has a conventional, some sort of battery, and let's say it's 10 volts just to keep it super simple, and I'm going to have some kind of switching system here so that I can have one side working or the other side working. A resistor and a capacitor. Now, and this is my charging side of the circuit. So when I connect up the circuit here, I'm charging. And when I connect up the circuit the other way, so I could have, say, positions A and B, this might be put in a question, I'll be discharging. And to keep it simple, I am going to just have the discharging to not have any extra resistance in it. So the discharging loop is simply a loop going the other way. And in a circuit like this, I'd put my ammeter somewhere like here and say, I'm going to measure the current here. So I would have an ammeter here and say, I'm interested in what is the current here. Now, conventional current, which goes from positive round to negative, goes that way around. So I would be measuring my current there. Okay, or you might say I could measure it here. It doesn't really matter. But let's say I measure the current there. Now, I'm going to go through the graphs of what happens over time from the moment we go from, maybe we'd have an intermediate switch here where we could just rest that switch. From the moment when we sort of connect it up to charge, then we wait, and then we discharge. So, and I'm going to go through the graphs of how that is going to work. So, okay, here's the first graph. So the first graph is simply the voltage across the capacitor. So I'm measuring the voltage here, VC, voltage across the capacitor. So on my first graph, let me just make sure that it's in shot. Okay, on my first, but quite simply, as time starts off, I'm going to use units of time here. And just say let's call them seconds for the sake of argument. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the highest voltage I'm going to achieve is the 10 volt supply voltage. And over time, and I've kind of arranged this to be at about 4 seconds. I'm trying to do my improvised exponential function that reaches the asymptote at 4 seconds. Now, the asymptote is math value for this value which it can't exceed. It might not be perfect use of the phrase from maths, because I thought in maths normally you can't actually get to an asymptote. Anyway, we're going to go up to 10 and then we're going to carry straight along. And then at some future time, say after 6 seconds, so I've charged in 4 seconds. After 6 seconds, if I switch the switch across now, so after 6 seconds I'm going to switch across from A to, I've now charged up, I'm going to switch it across to B, and I'm going to then discharge the capacitor now. And it's going to happen because this circuit has only got one resistor, rinse. When I use it this way, it's got one resistance. When I do the circuit for the discharge circuit, it's got this resistance. So the resistance and the capacitance are the same for both charging and discharging, which means the time taken should be the same. So if it took 4 seconds to go up, if I start at 6 seconds, I should be finished in another 4 seconds at 10. I'm mildly irritated with the way I've not quite got there and then kind of cheated. Okay, so that is charging. Now, if you think about this, if you think about from the computers or anything else, we'd have positive charge appearing on this plate and negative charge appearing on that plate. And if you imagine the flow of positive charges being where the current indicates on your ammeter, a positive current is a flow coming out of the positive terminal. I know it doesn't really exist, but let's just play along with that for the time being. Then, in that case, the current has been going that way. Now, when we switch over to position B, and we now have, that doesn't exist, and we have this, we now have the current flowing the opposite way. So previously current was coming this way, but now it's going to go that way. So the current graph that I need you to remember is different insofar as the current is initially large and in the same 4 seconds. So I should really have labeled my seconds. 5, 6, 7, 8, 9, 10. Time. My current is probably in amps, might well have been in milliamps. Okay, so my voltage I've measured in volts, and that's fine. So as I go along, at the time we switch it, then the current reverses, and because the resistance is the same and the voltage is the same, the current will reach the same height on the negative scale. So I've got my positive current, negative current, and if this value was, whatever this value was, this is exactly this opposite value. Okay, so let's say if this was 10 milliamps, then this is minus 10 milliamps. Okay, let me just slide that up as I realised I've just drifted off out of shot. So now technically that's been zero current, zero, whoosh. So we've got this sudden spiking up as I switch it on, and I've now got a large negative current, relatively speaking. And in 4 seconds, that is going to fall away to 0. So charging and discharging, the voltage stays on the same axis because the voltage rises and then falls. And there's a kind of folding over there. Perhaps you could work out if we flip that one over. And you think about the symmetry in that for yourself. And this one, the current is initially high and falls and then the current is initially high in a negative direction when it's discharging. Okay, so hopefully that patches the bit that I didn't put in the other lesson.